In the previous video, we found our eigenvector for our first eigenvalue for lambda equals 6. We now are prepared to do the same thing for lambda 2. And it's the same process. We just have to do it for a different lambda value. And in this case, we're going to have, again, our our eigenequation, a minus lambda I times v equals 0. And I suppose we could have really put lambda 1 and v1 over here, and this is for lambda 2 and v2. So our lambda 2 is negative 2, and again, a minus lambda I is 2 minus lambda, so 2 minus negative 2. These two values are constants, and then here we'll have 2 minus negative 2, plugging in our lambda, times some x, y vector equals the 0 vector. And so our matrix here becomes 4, 4, 4, 4. Once again, we see that the columns are linearly dependent. Same thing here. We can see that these two columns are negative 1 multiples of each other. Here they're exactly the same. So because we can scale one and get the other, this tells us that we found the eigenvalues correctly. It means we're going to have infinitely many solutions as we wanted. Because again, 0, 0 will always work here. In order to get more than just that trivial solution, the only options are a system can have 0, 1, or infinitely many solutions. If we now compute the reduced row echelon form of 4, 4, 0, 4, 4, 0, we're going to end up with 1, 1, 0, 0, 0, 0. And we can see that this is going to have infinitely many solutions as long as x plus y equals 0 and 0 equals 0. So any eigenvector we will require that x is equal to the negative of y. Now once again, there's no constraint telling us what y has to be, so because there's no information on what y has to be, we can say that it is a free variable. So again, y is a free variable. We'll set it equal to c, some constant. Let y equal c, and therefore our solution for this eigenvector, v2, is going to be that x and y, well, if y is c, x has to be the negative of that. So any vector in which the two have opposite signs but the same value represent an eigenvector. And so let's again choose something simple. I just prefer choosing 1 in general just because that's produces a clean looking vector for the most part. You could choose c equals 2, you could choose c equals 3. There are infinitely many eigenvectors that you can pick here, and we've already established that any choice of these values will produce an output that is just a scaled multiple of that input. So if I choose 1 for c, then I will have negative 1 for the x component, and this is in fact an eigenvector. Now we can just double check. If you put in negative 1 for x and 1 for y, negative 1 times 4, 4 plus 1 times 4, 4 equals in fact 0. So that satisfies the equation. Also, I should just be able to check, and this is just an extra side note here, if you did want to check that AV will produce a multiple of V for v2 and lambda 2. You can do the same thing for v1 and lambda 1. And in this case, our A matrix was 2, 4, 4, 2. And when I multiply that by the negative 1, 1 vector, I'm going to get negative 1 times 2, 4, plus 1 times 4, 2, which is going to produce 2, and negative 4 plus 2 is negative 2. And you can see that relative to the input vector, negative 1, 1, this is really negative 2 times the negative 1, 1 vector. And you can see that what we put in and what came out are just multiples of one another. And there's that negative 2, that eigenvalue. So this just means that we've done things correctly. So to find these, to solve, I kind of mentioned over here that you can use quadratic formula. It can become kind of painstaking to solve these and to have to find these values. You can use Wolfram Alpha to do it, and I encourage you to solve that characteristic, what we're going to call the characteristic polynomial. for lambda, we just used x here in place of lambda, and you can see that the solution to that is x equals -2 and x equals 6. So these are my two lambda values that we found. Lambda, I think we called this one lambda 2, and we called this one lambda 1. So let's do another example. And to point out, this thing was called, this quadratic polynomial we solved to get the lambdas is called the characteristic polynomial. Also, I want to point out that earlier we argued that a 2 by 2 should have 2 eigenvalues and 2 eigenvectors. We can kind of see why this is the case, because when you solve a quadratic equation, you're going to always get 2 roots. It could be the case that you get repeated roots or even complex roots. And complex means that you could get roots of the form a plus or minus bi, where a and b are constants and I is the square root of -1. We're not going to get into that, but you just note that you can get complex eigenvalues. All right, so find the eigenvalues and eigenvectors of a equals -6, 3, 4, and 5. So we're going to proceed in the same fashion. We know that to find these, we have to use the eigenequation, and the variant of it that we use is a minus lambda I times v equals the 0 vector. And so now if I take a, which is -6, 3, 4, 5, and I subtract away lambda I, which is going to give me again lambda 0, 0, lambda. So that's just this whole coefficient matrix here, multiplied by some xy vector equals the 0 vector. This in the brackets will come out to -6 minus lambda, 0, sorry, not 0, but 3, and 4 minus 0, and 5 minus lambda. And this is our eigenequation with our lambdas in there, and we know that we want the determinant, and I'll kind of continue off over here, the determinant of a minus lambda I, which is -6 minus lambda, 3, 4, and 5 minus lambda. We want to set that equal to 0. We're doing that so that we force the determinant to be 0, and if it is 0, the system will have infinitely many solutions. So again, we're going to compute the product, -6 minus lambda times 5 minus lambda minus 4 times 3, and solve for lambda while that's set equal to 0. So once again, we can pop over to Wolfram Alpha and do this. So here I have that input. I have it set equal to 0 for our determinant, and now I can figure out what the values of x are. So you can actually see it. It even shows you the parabola that this function represents, and you can see that those are the 2 roots that satisfy this equation. If we scroll down far enough, we'll see x equals -7 and x equals 6. Those are our 2 eigenvalues. So x equals -7, x equals 6. And again, it's kind of arbitrary which ones you call lambda 1 and lambda 2. Later on, we'll establish convention for this, but for now, it doesn't really matter what order we put them in. So now I have to go through the same process as before. I'm going to find v1, and I don't know what that is yet, but I know that that's going to correspond to lambda 1 equals -7, and then I'll do the same thing for v2 to compute it, but I'll use lambda 2 equals 6 to help me find that. So if I plug in -7 into this equation here, I'll have -6 minus -7, 3, 4, and 5 minus -7, and I'm going to solve for the x and y that gets mapped to the 0 vector. So in this matrix, I'll have -6 plus 7 is 1, 3, 4, and 5 minus -7 is 12. And again, you can see here that this 1, 4 vector and this 3, 12 vector are multiples of each other. If I scale this by 3, I get this. And you can even see that the determinant 1 times 12 minus 4 times 3 is 0. Therefore, the system is going to have infinitely many solutions. So I'm ready to solve this. And I'll have 1 times 12. My matrix will be 1, 3, 4, 12, augmented by 0, 0. Perform Gaussian elimination on that. And we're going to end up with 1, 3, 0, 0, 0, 0. So that means, once again, that x plus 3y equals 0, and we get 0 equals 0. So, again, here we see that y is a free variable. X just has to equal negative 3y. So we'll say that y is free. Let y equal c. And so then our eigenvector v1, our x and y components, well, y is going to be some constant, and x has to be negative 3 times that constant. So easy choice is to choose c equals 1. And so you pick any c value that you'd like, but if I choose c equals 1, then I will end up with v1 being equal to negative 3 times 1 and 1. And so there is an eigenvector for this eigenvalue. Again, I should just be able to check that if I multiply this vector by a, that I get exactly negative 7 times this vector as an output. That this vector will get scaled by negative 7 when I put it in. And now we can do the same thing, but for v2. So for v2, we'll have negative 6 minus 6, 3, 4, and 5 minus 6 times xy equals 0, 0. And so that gives me a negative 12, 3, 4, and negative 1. And at this point, again, I should just be able to confirm that the determinant is in fact 0. So negative 12 times negative 1 is positive 12. Minus 4 times 3 is 0. So that's a good sign. That means we're bound to get infinitely many solutions. So negative 12, 3, 4, and negative 1, augmented by the 0 vector. There's my constants. And if I perform Gaussian elimination on this, I'll end up with 0, 0, 0 down here. And this one will reduce to 1, negative 1/4, and 0 for those components. So again, we see that we get an equation that depends on x and y. X minus 1/4 y has to equal 0. And then again, I see that the second one says 0 equals 0. So this first equation just tells me that x has to equal 1/4 of y. Okay, x has to equal 1/4 of y. Y is again a free variable, so let y equal c. And now I'm not going to choose c equals 1, and the reason I'm not going to choose c equals 1 is because first of all, my vector v2, which is xy, is going to equal, if y is c, then x has to be negative 1/4 of that value. And the reason I'm not going to choose 1 is because then I end up with a vector that contains a fraction, and I'd rather pick a vector that is going to be easy to work with. So I'm going to choose, personally, c equals 4, because that's going to give me v2 equals negative 1/4 of 4 is negative 1, and then c is just equal to 4, so that keeps things non-fractional. So that was just a choice that alleviated me from having to record a fraction. And so now we have our eigenvector corresponding to that eigenvalue. So we've completed this example. In the next one, we'll take a look at a 3x3 matrix and see how this process works identically. But unfortunately, we're going to have to do things 3 times because we are going to end up with 3 eigenvalues. So we're going to need to record 3 eigenvectors.